We saw earlier that if we look at potential curves for DLVO theory, as a function, potential energy as a function of distance between the two particles. So we can have a secondary and a primary minimum. And that this energy peak here constitutes a barrier to coagulation. So particles are drawn together by the van der Waals interaction, but the electrostatic interaction provides a barrier that sort of pushes them back apart. And so while they might have this sort of weak interaction here that we call that you can call flocculation, they won't actually coagulate and have an irreversible so with the secondary minimum over here, we would have a reversible attraction. If we fall into this deep well over here, we can have an irreversible coagulation, and that can be prevented by this barrier here caused by electrostatic interaction. So we can imagine if we were to increase the amount of electrolyte in the system, that's going to shrink the Debye length and shrink electrostatic repulsion, and eventually this curve is going to look something like this, where this maximum is not rising above the zero of potential energy. Well, in that case, let's mark this as the zero of potential energy. In that case, coagulation will be fairly rapid. So the particles will come together into the secondary minimum and fall into the primary minimum. And at that point, the colloid's dead. It's irreversibly, all the particles are irreversibly stuck together. So the concentration of salt that will induce this, we call the critical coagulation concentration, or CCC. We want to know what concentration of salt that is. So let's figure out for spherical particles what concentration of salt will induce rapid coagulation. So to figure this out, we're going to go back to some basic calculus. We put our curve here that gives the so we have our DLVO curve that gives us the potential energy as a function of difference between this distance between the spheres. Let's go ahead and draw a little picture here. Just to remind ourselves, we've got spheres of radius r separated by distance h. For simplicity, we're going to be looking at identical spheres. That makes the math a little bit easier. Okay, so the expression for potential energy for spheres separated by some medium, and so we have spheres made of material 1 separated by some medium 2, and another sphere of medium 1. So perhaps we have two luminous spheres separated by water, dispersed in water. So the expression for the total potential energy in such a case is going to be pi times the radius of the particle, 64, the number concentration of the electrolyte in solution, thermal energy kT, got the potential cap gamma squared, e to the minus kappa h. Remember, kappa is the inverse Debye length. And then we have another term which is negative, which is the van der Waals attraction term. and we've got this surface potential term, which is going to be repulsive. Okay, now we know at the critical coagulation concentration, two things are true. We know that the total potential energy is equal to 0. We also know the derivative of the surface potential will be equal to 0 because we're talking about this little maximum over here. So since it's a maximum, the derivative is 0, and we're saying it's just touching that axis, and so the number itself is 0. So if we take these two equations, we're going to be able to figure out what concentration of salt will give us a 0 of potential energy. So let's do that. So first, we're going to look at this condition, and we can see that that means this whole equation is going to be equal to 0. So we can just put the two terms on opposite sides. And we're going to call this equation 1. On the next page, we'll look at the other equation, which says that the derivative has to be equal to 0. We're going to take the derivative of this, and it looks like a messy derivative, but actually it's not, because there's still little places that are dependent on v here, on h, the distance between the particles. So let's take the derivative with respect to h. You can see all these constants are here. We've got h to the -1, so the derivative of that is going to be a negative h to the -2, so that negatives are going to cancel. So we have h121r over 12h squared. And then we take the derivative over here, and really all these things are just constants. So we just rewrite the constants. None of these things vary with h until we get to the exponential. So we take the derivative of exponential, we get the exponential back. Take the derivative of the inside function, and we get minus kappa. Okay, so we know that we're at a maximum, so that derivative is equal to 0. And we're going to call this equation 2. And it turns out all this stuff is going to cancel, because if we go back to equation 1, the previous page, we can see that we've got this term is equal to this term. So if we can find those two pieces anywhere in the second equation, we can cancel them. So we go back, and we can see, aha, we've got this term here. So I'll circle it. Now I have to be careful. There's only one factor of h on the other one. So I have one factor of h left over on the bottom there. Over here I have all this except for the negative kappa. So since those are equal, we can just divide through by whatever their value is and cancel them out. So then we can write that we have 1 over h. So then we can write that we have 1 over h here, and here we have a minus kappa, and that's all equal to 0. So if we solve for h, we can say 1 over h is equal to kappa, or h is equal to 1 over kappa. And remember, kappa is the inverse Debye length. And so we could just rewrite this if we wanted to as h is equal to the Debye length. Okay, so that's a fascinating result, that the distance on this graph here, that this distance is going to be the Debye length. Okay, the distance at which the potential is going to just reach 0. Okay. Now what we really want to do is find out what salt concentration will induce rapid coagulation. But now we know what the distance is, we can plug that distance back in and solve for the salt concentration that will induce this condition of having a barrier to coagulation that's equal to 0. In other words, rapid coagulation. So we're going to plug this back into equation 1. We can see, well, let's just cross off r's on both sides. And then let's plug in the equation we just derived, which is that h is equal to 1 over kappa here. So now if we look at this, the only variable in here is going to be the concentrations. However, we have to remember that kappa itself is a function of how much salt is there, right? So we actually have to explicitly write out the expression for the inverse to bi-length kappa. So let's write that out. So kappa is going to be equal to, and rather than write this out as a summation, let's write a simplified expression that's only true for symmetric electrolytes. Otherwise, the math is going to get really messy. So for symmetric electrolytes, we don't have to have a summation for all the different ion terms. There's 2 ion terms, and they're identical, and we can just put them together. So what's in a symmetric electrolyte? Something like sodium chloride, where it's +1 and -1. Or something like calcium sulfate, where it's +2 and -2, etc. So all these would be examples of symmetric electrolytes. Okay, so for symmetric electrolytes, it's very simple. We have 2 terms, so we just multiply by 2. Each term, we've got the charge on the ions, we've got the concentration, we've got the charge on an electron, we have the number concentration, the dielectric constant for the solvent that we're using, and then the vacuum permittivity, and then the thermal energy. And because we're going to have E being used for 2 different things, here it's the charge on an electron, and over here it's going to be the logarithm base, we're going to actually just put this out as a number. Okay, so let's go ahead and plug this in over here and see what we get. And we'll see in a second, and we'll simplify to something much more tractable. Okay, so what we're going to do is take this kappa and divide both sides, put it over here, so we'll have kappa cubed, and then we're going to pop this expression in there. So we're going to take this whole expression and cube it. If we look at this over here, we have e to the -1, and since we have this is a base 10 or base natural logarithm, and this is the charge on an electron, we're just going to call this 2.71 rather than e to avoid confusion. So we write that, put that in here, we call this 2.71, and we have our original kappa now cubed. All right, so at this point we really only have concentration in one variable. So the electrolyte concentration is just captured in this number concentration. So all we have to do is simplify this and solve for C0. Easiest way to do this is to square both sides to get rid of that square root right away, because we're going to need to do that at some point. Might as well do that now. So get rid of the square root, and we can see now what we can do is we can take these parts and put them up on top. Let's go ahead and solve for C. C0 squared with all but one factor of C. Multiply both sides by C, and so we're going to solve for C that way. So multiply by C, divide by the Hamburger constant squared, multiply by 144. So the convenient thing about writing it like this is we can circle all this, and these are all just numbers. And we plug those in, and we get, so the critical coagulation concentration in terms of number concentration, in terms of ions per cubic meter, is going to be approximately equal to, we said, roughly 99,000. So let's just say 10 to the 5th times this collection of constants over here. So it's just strongly dependent on the temperature and the dielectric values. Remember, this term is a function of surface potential, and then inversely proportional to the 6th of the charge on the ions. And so that is the critical coagulation concentration.